Okay, hello everybody. It's a pleasure to be here today and also visit this very historic and beautiful city. It's also a pleasure to be this exciting and beautiful university. What I'm going to talk about today is about some work we have done recently, where I tried to ask the following question. If one of the most popular models for explaining the Hubble tension is the reduction of the sound horizon scale, which automatically also increases the Hubble parameter. So if this model was in fact complete, then the rest of the measurements of the Hubble parameter should be self-consistent and highly consistent also with the distance ladder measurements of the most precise one that we have from the Cepheids. So the question is, what happens with the rest of the measurements which are independent of the sound horizon? Are they self-consistent? And are they consistent with the most precise measurement we have for the distance ladder Cepheid measurements? So that's what I'm going to talk about today, which is an exercise I recently did, and is published in this work. So where I try to compare these sound horizon free measurements and see if they're self-consistent and if they're consistent also with the distance ladder measurements. So the motivation, as I said before, is that the fact that there are two approaches right now to the Hubble tension. The one is to try to modify the sound horizon distance calibrator, which increases the CMB and BAO H0 measurements if we decrease, of course, sound horizon scale. And the second approach is to deform the Hubble parameter H of Z using, for example, late dark energy or late modified gravity, so that the sound horizon calibrated H of Z increases and again becomes consistent with distance ladder measurement. Now, these are the two approaches. The approach 2 has some serious challenges in the sense that the low Z supernova data, which are calibrated with Cepheids, are not consistent with the low Z BAO data, bioacoustic oscillation data, which are calibrated with the sound horizon. So we have two calibrators, and this you can see, for example, in this, they cannot be simultaneously fit unless the two calibrators change. Here you see this well-known plot with, here you see the H of Z over 1 plus Z, and you see this is the Rees et al. Point, the well-known, and there you see that one way is to try to deform this H of Z using late dark energy. However, in this case, the supernova which are calibrated using the Cepheids still are inconsistent with the bioacoustic oscillation measurements which are calibrated with the sound horizon. And so even in this case, even if you manage to fit this H0 from this distance ladder, you still have problems to simultaneously fit at low redshifts both the bioacoustic oscillations and the supernova, which are calibrated in different ways. So this tension remains there, and this is a well-known thing. And the question is, so most probably we will have to either change the calibrator of Cepheids, which would lower, or any calibrator will use distance ladder, which will lower supernova data, or change the sound horizon, which will increase the bioacoustic oscillation data, so they can be made consistent. So this deformation does not seem to have problems, and other problems also, but this is the main problem, which to simultaneously fit this data. So approach 1, which is the sound horizon change, is more popular. However, there still are some problems with this, which is summarized in this paper by Stan Ivanozzi. However, its main issue is that it's still, what happens with the other measurements of H node, if they are not in agreement with the measurement of distance ladder, then any kind of change of the calibrators of sound horizon will increase this curve and will probably miss other measurements which I will show that in fact they are lower than the distance, distance ladder measurements. So the question is this assumption realized by recent one-step H0 measurements? That is, are they consistent with distance ladder measurements? So this is the exercise that I tried to do. Here you see a plot that we have recently in this CosmoVerse white paper, which shows the early time measurements based on sound horizon, bioacoustic oscillation and CMB. And it's compared with two classes of measurements. What is here it's called direct measurements, which basically are distance ladder measurements. And these are called modeled phenomena measurements, which are basically one-step measurements based on other non-distance ladder, non-calibrated, non-independent of local astrophysics. So these are mostly distance ladder measurements, and these are one-step, I would call them one-step or really direct measurements because they do not involve local astrophysics. Now, this list of what is called model phenomena here is in fact incomplete. There are many more measurements here, and I will try to show them today. And the question is, would they be in agreement with these measurements of distance ladder? So if we put all the measurements here and the assumptions, would they be in fact consistent with distance ladder measurements? So one question is, what is a more complete list of measurements? And what is their are their statistical properties? And this is the issue that I'm going to try to discuss today. So let me review briefly the methods for measuring H node, which is one is classes the distance ladder measurements, which compares the apparent magnitude of supernovae with the absolute magnitude and the luminosity distance. This can be expressed in this way, where we have this measurement here, and the Hubble free luminosity distance and the Hubble parameter here. What one can measure is in the Hubble flow is this combination here of the absolute magnitude and the H node. So we have a degeneracy between M absolute magnitude and H node, which has to be broken by using measurements, local measurements of the absolute magnitude of supernova using Cepheids or other calibrators or the TRGB, etc. And if we break this degeneracy and fit the Hubble free luminosity distance, for example, using a cosmographic expansion, we can fit H node as is well known. And the fit assumes, of course, that this M, which is fit using very close local astrophysics physics, is the same as the Hubble flow. And that's a big assumption of the all distance ladder measurements, that this M measured locally is the same as in the Hubble flow. So here there are assumptions. It's not really so much direct. There are assumptions which need to be taken into account. And however, in this case, there is no real model dependence because you have this cosmographic expansion, but there is still this assumption. Now, this is the well-known result that is known from Adam research and the SUSE collaboration. The other method is using the South Horizon Standard Ruler, which one measures, of course, the angular scale of the South Horizon compared with the South Horizon scale, and has this degeneracy between H node, the South Horizon scale, and this co-moving angular diameter distance from 0 to the last scattering surface. And one can calculate, of course, RS, South Horizon scale, and also assume a lambda CDM form for the EZ. And one can see that there is degeneracy between H node and RS, and also with this co-moving angular diameter distance. And if one decreases RS, assuming, for example, early dark energy here or other effects, one can increase H node given this measured theta s, or if one can increase this angular diameter distance and increase also H node. So there are two ways to do that. Either you deform H of z from the denominator so that you increase this denominator, or you decrease RS, and both of them increase H node given this measured theta s. So this is the result for the standard model. You see this 67.36 from Planck, which is well known. And there's degeneracy between RS, H node, and E of z, of course, and this corresponds to these two methods that I showed before. On the other hand, one-step methods, which are independent of the distance ladder, are other methods which are not calibrated with local astrophysics. And these are, for example, time delay gravitational lensing, megamasers, gravity waves, cosmic chronometers, and the horizon at the time of fecal matter and radiation. And the question is whether these methods actually give you different results, or if they give you results which are consistent with one of these two different approaches. So what's the H node for these measurements? So the main question is, what are the current distance ladder measurements of H node, and if they are consistent with the SUSE measurement? And the second question is, what are the currently available one-step measurements of H node, which are independent of both sound horizon scale and distance ladder, are they consistent with each other, first of all, and are they more consistent with SUS or with the sound horizon measurements? That's a key question to understand a little bit better how to proceed with the models of the Hubble tension. So I made a large compilation of the existing measurements of this type, which are no sound horizon and no local calibrators, so independent of distance ladder. And you see here that these measurements, starting from about essentially 2020, but I've put some earlier measurements just for completeness to compare with some of these later measurements. But after 2020, these are most of them. There are 33 measurements using various methods, as you can see here: cosmic chronometers, gravitational waves, T-quality standard ruler, fast radio bursts, lensing, TD Cosmo with slacks or not, megamasers, etc. And all these measurements, you see, many of them, most of them actually start with a 6. There are some of them start with a 7, but most of them are lower than what distance ladder measurements would predict. This was an interesting observation to make, and one can actually look at them. There are actually two outliers here, as I will show before, later, because I compared this chi-square, and this is the TD Cosmo 1, and the megamasers, which are not so much consistent with the others because they're extremely precise. One of them, the lensing TD Cosmo 1, has been shown to have some systematics in it, because they have used some assumptions about the lensing potential, and it has been shown in some later publication of theirs. So this is discussed again in this paper that I have published recently. Now the next thing is the distance ladder measurements, these are summarized here, starting from about 2020 and later. And you see that essentially all of them, almost all of them, start with a 7. Which means that they're consistently higher than the other measurements. And of course, there are various types of distance ladder measurements. They can be based on various distance indicators, like Myra calibrators for Tully-Fisher, etc. Even though we have various different approaches for this calibration and for the distance indicators, they all seem to be higher than the other one-step measurements. And in fact, the weighted mean of distance ladder measurements is 72.8 plus or minus 0.5. And one-step measurements without sound horizon have a mean of 69 plus or minus 0.5. And if we remove the two outliers, over here I showed, it goes down to 68.3 plus or minus 0.5. So we have a consistent lowering of the Hubble constant if one uses one-step measurements compared to if one uses distance ladder. So again, this is no sound horizon. There is no dependence on sound horizon here. It's completely. And this is by year. You see the blue points correspond to one-step measurements, and the red points are distance ladder measurements. These are all the measurements, and these are the measurements by year averaged. And you see that consistently the blue points are below the red points for all years after 2019. With the exception of TD Cosmo 1, which is higher in this year, in this 2019. So this is the distance ladder SUS point, SUS measurement, and this is the CMB measurement. And you see that based on one-step measurements, we have consistency with the CMB every year, almost. And while the distance ladder measurements are consistently within this pink area, which is the average for this. So the distribution functions can also be discussed. You see that here for the distance ladder measurement we have this kind of probability distribution, while for the one step we have this one. And one can do a Kolmogorov-Smirnov test and see that the probability that they are both drawn from the same probability distribution is less than 0.01%. But this is more or less to be expected because these measurements are much more diverse than the distance ladder measurements, so it's not a big surprise, but anyway, it's something to note. Now, one can actually split the samples into various parts. For example, this full sample, as I said, has a H-node 69.0 plus or minus 0.5, but the chi-square per degree of freedom here is somewhat large, is 1.37, so it means that there's some internal tension between them. But if we exclude the two outliers, the megamasers, early megamasers and the TD Cosmo 1, we get a much better chi-square per degree of freedom, which is 0.95. In any case, we can do play various games here and see which measurements pull in various directions by excluding, for example, cosmic chronometers give a measurement very close to the sound horizon indicated measurements. Megamasers seem to be a bit higher. We have various other cases to look at. So this is the one-step measurements become self-consistent and are fully consistent with the sound horizon scale if the two outliers are removed. That's an interesting observation. Now, since the paper was appeared, which was about September 2000, last year, a few months ago, there have been several other measurements which have appeared. In particular, there has been this time delay TD Cosmo 225 measurement, and various lensing measurements, etc., the fast radius of bursts, etc. here. And one can use the weighted mean of these measurements and see that they are about 70.4 plus or minus 1.2 kilometers per second, which is consistently lower than distance ladder, but still it's a bit less inconsistent than previous measurements. So the implications of this observation is that H0 measurements are independent of local astrophysics, are consistently lower than distance ladder measurements, so this is one observation to make. And the theoretical models that are based on modifying the sound horizon scale should have to simultaneously fit distance ladder measurements and these one-step measurements, which is somewhat challenging because these are lower than the distance ladder measurements. Now, it's possible that some physical or systematic effects on distance ladder calibrators realized through astrophysics probably play a role in the resolution of the Hubble tension, since all other measurements, except the distance ladder, seem to be lower than the distance ladder measurements, so it's something to look at. Now, so some possibilities is, for example, screen fifth forces on the cosmic distance ladder. Maybe the gravitational constant behaves differently on local scales because of screening. That's one possibility. Also, another possibility is to have a rapid transition of the gravitational constant, which could, for example, also induce some change of different behavior in local astrophysics compared to the Hubble flow case. Or there could be some systematics. For example, we have another paper recently which shows that if one isolates only blue type 1 supernova in the distance ladder, one can get less effects of dust, of course, and therefore one shows that one get a lower value of H naught than the other distance ladder measurements. Okay. And so here is the possibility of here I show, for example, the case of a local physics transition. In that case, if you have a change of gravitational constant at some rates of about 0.01, one would expect to have a larger value of m, of the absolute magnitude of supernova in the Hubble flow, and that would bring it in agreement to inverse distance ladder calibration of supernova based on the sound horizon. So this could be one possibility. Another possibility, and in that case, if this was the case, one should look in the distance ladder analysis for this effect by repeating the analysis of the SUSE collaboration, allowing for a change of the absolute magnitude at some particular distance. And if we derive μi without allowing such a transition, the original SUSE approach, we get this usual effect. You see that these are the absolute magnitude of supernovae within the Cepheid region, where there are Cepheids and supernova hosts, and you see you get this kind of absolute magnitude. But if you redo the analysis, allowing but not enforcing a transition, you get at about allowing transition at about 50 megaparsecs or 45 megaparsecs. Then you get that these two last points spontaneously become lower and consistent with the inverse distance ladder. So there is some hint in the data themselves. If you allow this degree of freedom, you may get some different kind of behavior. So the main points of this talk are the following. First of all, that the Hubble tension is a tension between distance ladder measurements and most other measurements of H naught. So one can see this kind of view based on this analysis. The second is that the resolution of the Hubble tension may require a reanalysis of the distance ladder measurements, including introducing new degrees of freedom. For example, a possible change of the absolute magnitude of supernova at some distance, and this could be as a new degree of freedom for the identification of new physics or systematics. A transition could, in principle, resolve this puzzle if it happened at about set transition about 0.01. And there are hints in the issues data for such an ultra-late physics transition. Thank you for your attention.
Questions?
Hi, nice to talk. So you talk about shoes, maybe there possibly being some transition right at 50 megaparsecs, which...
Yeah, I'm not saying this is a possibility, I'm just focusing on the data. I'm not saying that this is necessarily the resolution of this puzzle, but it's...
Sure.
Yeah.
So now that, in the last talk we heard about surface brightness fluctuations, and there's Tully-Fisher, there's a lot of other techniques that cross the 50 megaparsec thing. Does it make sense to focus on shoes as kind of the thing?
No, it doesn't make sense. I'm just saying in general, any analysis should allow this kind of degree of freedom to make sure that there is nothing peculiar happening at 50 megaparsecs or at 40 megaparsecs. So in the analysis of the data, it would be interesting, instead of assuming a fixed value of the supernova absolute magnitude, to allow for this possibility and see if the data provides some hint of that. I'm not saying that necessarily the shoes analysis would have to do that. Of course, I'm saying that any analysis should try to allow this degree of freedom. Of course, we did it for the shoes data, but it should be done. It could be done also for other kinds of data.
So thank you for the nice talk. So you proposed some solutions, but you didn't mention local void. I think local void hypothesis is local void solution.
Local void, yeah, that's right.
Yeah, I think what this show, it actually you can interpolate as a local evidence for local void solution, if I understand. But
yeah,
you didn't show it in your solutions.
You're right. I mean, that's a possibility, but it's just a common belief that perhaps the void solution is very hard to achieve within the lambda CDM framework. I mean, of course, it's a possibility, but within lambda CDM, such a huge and deep void is unlikely. So if you want to keep the framework of lambda CDM and only put a void in that, my understanding is that it's not so easy to have such a deep void to achieve that. But again, it's also an open issue. Yeah.
Let's thank Leandros again.